flips in 9 coins. So H we have here, we have 5, the probability of X being more than, so that's a greater than 5. Well, again, calculator doesn't do greater than, therefore we can't do this on our calculator. We have to turn this around. This is 1 minus the probability that X is less than or equal to 5. So again, let's take a look at a distribution function right here, probability distribution histogram. So here would be my histogram, right, for going forward from 5 and then down from there. And I'll just kind of, sketch it in here. So greater than 5, that would start up when the 5 bar ends, and it would get all these, wouldn't it? So if I'm thinking about the complement is the 5 bar and everything fewer. So this is what I said, 1 minus and then the 5 bar and fewer. So that's what the complement looks like. So I can do this on my calculator as binomial CDF, and I do ask that my students actually write out these notations so I know exactly what they did and how they got their probabilities in case they put in something wrong. I can kind of figure out what I can do to help them if I'm making notes to them, and that's especially true on a test. So this would be 1 minus the probability, and so I'm going to do my second function variables up to the binomial CDF, making it sure it's the CDF, putting in 9 for my number of trials, putting in 0.5 for my probability of success, P, and 5 for my random variable X. And that gives me 0.74609,375. Rounding it to 3 decimal points would be right there, but I'm going to need to actually subtract from 1. So I'll say that this is point, and that would be 2, 5, 3, 9, 0, 6, 2, and then 5. So I can round it to right there. So this is approximately 0.254. And that would be the probability of being greater than 5. So that would be what I'm looking for. And that wraps up that example. All right, now moving on. This is the binomial probability table. And so this one, I'm going to just skip this example because I've already shown you the table. And I've already closed it down, so I'd have to add it. I have to open it up. And this is not as applicable, and the book doesn't spend very much time on tables anymore at all. But just know how to use that table and think of it just like a probability table. I usually don't give any table examples for binomials, but it's good to know how to relate to a table. So let's move on to this next question here. So a student comes underprepared or unprepared to an exam, so they will be guessing on each and every question on a multiple choice exam. So if they're coming guessing, the probability that they will get they'll get a problem correct is going to be a 50-50 chance, right? It's guessing. Or if it's multiple choice, 1 chance in how many ever outcomes there are. So each and every question on the multiple choice exam. So it's multiple choice, so because it's multiple choice, I have to know how many choices they have, and that's going to help me to say, oh, the multiple choice, there's A through E, A, B, C, D, and E, that's 5 different choices. So the probability of a success is going to be 1 in 5. That's the right one, right? There's 1 answer in 5 that are right, which leaves there's 4 in 5 that are wrong. And then the number of trials, that's the number of problems here. So it's very important that we understand that we have to be able to recognize this as a binomially distributed random variable. So let's just run through those characteristics really quickly. Number one characteristic, there's a fixed number of trials, right? Fixed trials, and that's, yes, we have 10 questions. There are 10 questions, that's a fixed number of trials. Every person that takes the test, or every time you take the test, you're going to answer 10 questions, aren't you? And then the next one, there is a constant probability. Well, this relies on the fact that we're actually guessing and that no problem is related to another. So constant probability, yes, there is constant probability, and that probability of a success is 1 in 5, right? And then also that there's only 2 outcomes. And those 2 outcomes, yes, you either get the question correct or incorrect. Now, this one can sometimes be misidentified because it says that there are 5 different possible answers. Well, I don't care that there are 5. All I care about is the fact that there is correct and not correct. Whatever the other answers are, what they are, but they are incorrect answers. So that's the key. And then 4 is that every time that you take this test, it's going to have the same outcomes as the time before, because obviously you're guessing. So, and nobody's affecting each other's outcomes and blah, 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 blah. So the independence gets a little bit complicated. And as long as you come up with something about the trials being independent, right, then I'm okay with it. And you just kind of have to validate that trials don't influence others. So one person's taking the test, or you're taking the test one time from another, it's not really going to influence the outcomes. So that's how you tell that this is binomially distributed, and that's really super important because later on you're not going to be in the binomial section, and it's not going to be some indication that, oh yeah, this is my binomially distributed random variable. All right, so moving on here, I want the probability that this student gets a C or better. So I have to think about what is getting a C. Well, if I have a 10-question test, then a C out of a 10-question test is 70%, and so it's 70% of 10. And you can't get 75% on a 10-question multiple choice test. It's either you get 0 right, 1 right, 2 right, so on and so forth, right? So 70% of this means you get 7 right. So what we have going on here is the probability of getting a C or better. Oops. I think that I need to erase. Probability of getting a C or better here is the probability of getting a 70 or an 80 or a 90 or 100%. So it's a probability of getting a 7 or larger. So this would be 1 minus the probability of getting a less than 7. And therefore, because I need to turn that around to using my calculator, the probability of getting a less than or equal to a 6. So now that I have that, my stupid tablet did it again. So let's see if I can fool it, and I don't know if I'm going to be able to. So I think I'm going to have to break here, and then I will start up again in a new video. All right, so I will see you in the next video.